3 is next Wednesday. That would be the 27th. And it's not going to cover all of 2D kinetics. The topics will just cover the things up through, like the concepts up through number 9 of particle kinetics. Okay, so the rest will be on the next test. Anybody have any questions about the test?
So if we go up through the pulley content.
I don't have written down here what number 9 is. Maybe I have it. There is not going to be any pulley stuff on it. There is going to be some very simple pulling type problems. Is that right? Like the example that I did last time. We did that example, but there will not be anything like that on there either. Only stuff like in those first 9 problems. Okay, so all that other stuff is for later exams. Any other questions about the test? Yeah. Yeah, for sure. Yep. And remember that these tests are cumulative too, so be ready for old stuff too. Yeah. Yep. Everything up through number 9 in particle kinetics. Any other questions? Okay. Anybody have any homework questions? Okay, great. Okay, so in this one, it's a circular motion, and you have an object that at the instant we're looking at is at the top of the circular motion. This is the center of the circular motion. I'll call that point C. The object has a clockwise angular velocity of 8 radians per second. And the radius of the circular path is 0.4 meters. It doesn't say anything about an angular acceleration, so we're going to treat that as 0. And the coordinate system that we're using is given like this. We usually use. What's the acceleration of the object at the instant shown? So let's say that it's at the location P. So we're looking for what's the acceleration of that point P. And remember, it's important to keep in mind that that needs to be, if it doesn't say what the acceleration is relative to, then you're assuming that that's relative to ground. And I say that because we're going to have to use relative motion for this. And we're going to have to use relative motion because the center C is accelerating. So, well, the acceleration of that point C is 6 negative 2 meters per second squared. That's given. And then what's the net force on the object? Well, we know that we're going to use, to find that acceleration, we're going to use the fact that the acceleration of p relative to the ground is equal to the acceleration of p relative to the center plus the acceleration of the center relative to the ground. This one is given, and this one is circular motion. Okay, so let's figure out what we know about the circular motion. So the circular motion part is to calculate the acceleration of p relative to the center. So for this, since it's relative to c, we're just treating the center like it's fixed, and we're trying to figure out the acceleration of this point p. The angular velocity, I gave it before, is 8 radians per second clockwise. And that means that the velocity vector is this way. There's no angular acceleration, so there's no tangential acceleration. The centripetal acceleration is this way. And since there's no tangential, that's the entire acceleration. The magnitude of the centripetal acceleration is omega squared times r. And so that's 8 squared times 0.4. So 0.4 times 64 to 25.6. Meters per second squared. And now we know the direction is in the negative y. So the total acceleration is 0, negative 25.6 meters per second squared. And that's also the total acceleration because there's no tangential. Stop me if you have any questions. Anybody have any questions yet? Yeah.
On the exam, if you don't indicate relative motion, can we still use it? Like if it's not indicated.
If you don't write this equation out, you mean?
Yeah, like do we have to do it relative motion like this one, even though you don't ask?
Well, yes, you do have to use it because if it asks for the acceleration of p, that's implying that it's the acceleration of p relative to the ground that we want. And so if you didn't use relative motion, this would be your answer for the total acceleration. But this isn't the complete answer, you know? So now going to the relative motion part, the acceleration of p relative to the ground is equal to the acceleration of p relative to the center plus the acceleration of the center relative to the ground. Acceleration of p relative to the center is the one that's 0, negative 25.6. Acceleration of c relative to the ground is given as 6, negative 2. And so the only correct answer for this is 6, negative 27.6. And if you tried to use Newton's second law to calculate forces based on just that acceleration of p relative to the center, you'd get the wrong answer because it's not an inertial coordinate system. Okay, because you can't have a coordinate system that's accelerating and still have Newton's laws work.
That's the only time in circular motion that we cannot use the inertial coordinate system, right? Like be circular?
Well, so inertial is what you do want to use. Inertial means it's not accelerating and not rotating in time. And so anytime, anytime that the center of your circular motion is accelerating, you can't use that acceleration by itself. You're going to have to use relative motion. Okay, so that's part A. And then part B is pretty easy once you have that. Newton's second law says F net is equal to the mass times the acceleration of the center of mass. This is a particle, so the center of mass is just and so this is equal to 0.2 kilograms times the acceleration of p. And so that's equal to 1.2, 55.2, 5, negative 5.52. And that's a force, so this is newtons. And using Newton's second law, you almost always have to draw a free body diagram. The reason you didn't have to in this case is because we're just looking for F net. The free body diagram helps you break it up into the individual forces. Okay, so if you're not breaking it up into individual forces, all you do is multiply by m. There's not really any point in drawing a free body diagram. Any other questions about that one? Any other homework questions? Yeah.
It says it's about the cable that we didn't talk about.
So this one is a view from above. You have an object connected to a cable, and it's swinging around in a circular motion across ice, so we're assuming that there's no friction. The fact that this is a view from above means that when we deal with the weight force, that's going to be pointing into the page. The normal force is going to be pointing out of the page, and so those aren't going to show up in our coordinate system. The tether has a length of 0.5 meters, and so that's the radius. Hi. All right. So we have this block connected to a tether, and it's sliding around a circular path on ice. It doesn't say which direction it's moving, so let's choose counterclockwise because that's a positive rotation. And it makes one revolution every 1.5 seconds. So what are we going to do with that? One revolution every 1.5 seconds. That's right. So we have the rate of rotation, the angular velocity in terms of revolutions per second. And you can think of this as a unit conversion where one revolution is 2 pi radians. And so you get 4/3 4 pi over 3 radians per second. The mass of the block is 2 kilograms. We want to calculate the net force. And so now let's think about this as a circular motion. The velocity vector is this way. It's in uniform circular motion. What does that mean about the angular acceleration? 0. Yep. The centripetal acceleration is this way. And so that's also the direction of the total acceleration, or that is the total acceleration. The magnitude of the centripetal acceleration is omega squared r, and that's 4 pi over 3 squared times the radius is 0.5. So that's 16 pi squared over 9 meters per second squared. On a test, if you, I mean, I just don't have a calculator in front of me, but if you want to convert that to a decimal, that's fine with me. And so if that's the magnitude and the direction is straight up toward the center, which I'm going to call my positive y direction, the centripetal acceleration is 0, and then the y component is 8 pi squared over 9, and that's the total acceleration. And now finally, the net force, Newton's second law, says F net is equal to the mass, 2 kilograms, times the acceleration vector. And so that is 0 for x, 16 pi squared over 9 for y. And it's all SI units, so that's newtons. Okay, I have 2 questions about this. The first one is just sort of like a understanding type question. And the second one, I'm going to redo a calculation as if the question asked for something different. The first one is, this problem looks a lot like the last problem we just did. Why in that one did we have to use relative motion, and in this one we didn't? Yeah, because when you use the circular motion equations, they are treating the center of the circular motion like it's fixed, okay? And so if the center of the circular motion is fixed, like in this case, that's just like a stake stuck into the ice, then circular motion gives you the actual accelerations relative to the ground, okay? But if that point isn't fixed and it's accelerating, that's when you have to use relative motion, because circular motion gives you answers that assume that's fixed, and then you have to correct that answer using relative motion. Okay?
Because it's automatically attached to the pole from the box, right?
In this case, yeah, the key thing is that pole is fixed. Okay. If this thing was a sheet of ice with a stake, and that was on the back of a flatbed truck that was accelerating, then you'd have to use relative motion to deal with the fact that that stake is accelerating relative to the ground. Okay. Yep. Yeah. Oh, that's fine. That's great. So, and do a calculation? Oh, yeah. Yeah. Yes. So if center of the circular motion had an acceleration relative to the ground, of 5, -10. Then the acceleration of the box relative to the ground would be equal to the acceleration of the box relative to the center, plus the acceleration of the center relative to the ground. And that would be equal to, so the box relative to the center is what we calculated, 0, and then 16 pi squared over 9. And the acceleration of the center relative to the ground is 5, -10. And so you get 5, 16 pi squared minus 10, 16 pi squared over 9 minus 10. Oh no, that was the force, wasn't it? If we're talking about the acceleration, sorry. The acceleration just had the 8. The 16 came from when we multiplied on the mass. So this would still be 8 pi squared over 9. And then to get the net force acting on the box, you'd multiply that acceleration by the mass. Okay, now here's an extra question. What's the tension in the cable? Okay, so what this question asked was just what's the net force, but now we're going to break up that net force into its individual pieces and calculate one of those individual pieces. Okay, so for this, we need to draw a free body diagram of the box. And we're still doing it from above with the same coordinate system we've been doing. Forces act on the box. The weight, yep. Yeah, whenever I ask what forces act on something, be the first one to say weight. That's the easy one, and then then the other suckers have to answer the hard ones. But Daniel's done, see? Yes, okay, so what's the direction of the weight from the view that we're taking? It's, yeah, and on this picture, it's straight into the page. It has a mass of 2, so the weight force is 2 times 9.81. Okay, and then the normal force, what direction does that point? Yep, out of the page. And we don't know the magnitude of that, although we could calculate it. And then the tension force that way, exactly, toward the center. Okay. And now we'll go to Newton's second law. And each one of these forces, we have to consider in Newton's second law. Well, it turns out that these two don't show up in our 2D, the 2D that we're analyzing. So we have, 0, 0, and then a component in the z direction, plus 0, 0, plus that t is in the positive y direction. And that's equal to the mass times the acceleration.
Why is it 0, 0 instead of like 0, -9?
Because our coordinate system has the z-axis like that, the x-axis like that, and the y-axis like that. Okay, and so that means that if we were doing this as a three-dimensional problem, our weight force would have a z component of negative 19, 0.62. Our normal force would have, that's in the positive z direction, so we'd have normal like that. This one would be 0. The acceleration would be 0, and we could use that to calculate the normal force, but we're not asked for that, and so we're fine the way it was. So these are like the z components that we're ignoring. Okay. So the x equation, if any of you missed the class last Wednesday, we talked about the fact that 0 is equal to 0. This reinforces that, so if you weren't here. Other than that, it's not very helpful. The y equation says 0 plus 0 plus t is equal to 16 pi squared over 9. The z equation we're ignoring, and so this tells us that cable tension is 16 pi squared over 9. So what that says is, you go to the tackle store or whatever to buy the fishing line that you're going to use to swing this around. You need to get a fishing line that can handle that much force. And if you don't, it's going to break. Any other questions about that? That's right. That's right. I went back to the original question. That's right. Question?
There's no acceleration. It's not like accelerating, so that's why there's not X.
Right. The speed isn't changing. All the acceleration. So think of. So let me sort of summarize this. So the acceleration is 0 if the velocity is constant. Okay. So if the velocity is changing, there has to be acceleration. Okay. And velocity has two things. Like any vector, it has a magnitude and a direction. So there's two ways that the velocity can change. Its magnitude can change, and that's speeding up or slowing down, or its direction can change. In this case, the magnitude staying constant, the only acceleration comes from the fact that the direction of the velocity is changing. It's turning. Any other questions about that? Yep. You don't have to carry them through the answers, but they have to be on your, you don't have to carry them through your calculations, but they have to be on your answers. Okay. But I mean, on tests and stuff, I put everything in SI units. So all you have to do is know whether it's a force, then it's newtons, or a mass, then it's kilograms, or acceleration, velocity. So it's not too complicated, but you have to put it on your answers. Yes. Yes, tension has units of newtons. And if you ever don't know what something is, like you get to a tension and you're like, oh, what is this? Like what are the units? Well, just put the units in all the things that you use to calculate it, go through the algebra, and it'll tell you what the units are, Like this is kilograms. Force is sort of a complicated example, about as complicated as it gets, but this is mass, this is kilograms. This is acceleration, that's meters per second squared. Multiply them together, and you get that T has units of kilogram meters per second squared. Well, that's mass times acceleration, so it has to be newtons. It has to be a force. Okay, instead of going on to any new stuff, let me say one more thing. So here is a question. First a statement, and then a related question. Earth is always rotating, meaning points on the surface of the Earth always have centripetal acceleration, right? Because every point on the Earth is moving in circular motion. That means that coordinate systems fixed to the surface of the Earth are not inertial coordinate systems, right? Coordinate systems on the Earth's surface aren't inertial. Why doesn't that mess up our experiments on the surface of the Earth? Why doesn't that make Newton's laws appear to be violated on the surface of the Earth? Seem to fail on the surface of the Earth. Anybody have a guess, a hypothesis? It's not really that, because so normally, I mean, we just use like when we set up a coordinate system for an experiment, we just assume that this table has no acceleration, so we use it like it's an inertial coordinate system, and we see that Newton's laws seem to work. We just ignore it. So why do we? And it works. So why? Okay, well, here's the answer. No, that's not why. Because anything moving in a constant circular motion still has acceleration. Yeah, it's because it's so slow. So think about so omega for the Earth. We just did this problem that was one revolution every 1.5 seconds. Omega for the Earth is one revolution every 24 hours. And so one revolution is 2 pi radians. 24 hours, I believe that's 86,400 seconds. Okay. So those cancel. And can someone punch that into a calculator? 2 pi over 86,400. Give it to me in like scientific notation. Well, any notation is fine. Pi over 43,200. And so what is that about? I mean, I just want to point out how little that is. Times 10 to the minus 5 radians per second. And then to calculate the acceleration, well, now the radius of the Earth is really big. I can't remember what let's say it's 1 times 10 to the 6th meters. I think it's something like that, about 1,000,000 meters. But the centripetal acceleration magnitude then is 7.27 times 10 to the minus fifth squared times 1 times 10 to the sixth. And so that's, about 50 times 10 to the 10th times 10 to the minus 10th times 10 to the 6th. So this is 50 times 10 to the minus 4th, somewhere around there, meters per second squared. And you have to have a very sensitive experiment to be able to detect an acceleration like that. Yes. And the most famous one is called the Foucault pendulum, that I assume is in France somewhere because of how it's spelled. But and with that, you can watch, as if you watch this pendulum move over the course of a day, you can see that the plane of its rotation just gradually rotates in time. But like, for example, the kind of experiments that we do with our equipment in a physics lab or whatever, we can't measure something like that. So that's why we just gloss over the fact that the surface of the Earth is not inertial. Okay, see you tomorrow.